Hello, and welcome back to the video lecture series for ECE-340, Engineering Probability, Random Variables, and Random Processes. I'm your instructor, Dr. Bradley Duncan. Today we're going to talk about conditional probability. This will be an introduction to conditional probability. We're going to come back to the topics of conditional probability many times over the semester. My observation has been that conditional probability is one of the more challenging concepts for students to get their minds wrapped around. So I'm going to introduce it very early, introduce it with what I believe are some relatively simple concepts. We'll come back to conditional probability time after time after time. Throughout the semester, we'll go deeper and deeper and deeper. But today, I want to do some simple examples. And I'm going to be referring quite a bit to Table 1-2 out of the Cooper and McGillem textbook. It's on page 10 of the third edition of this book. Here's the table that I've reproduced for this video. And what we have here is a collection of resistor, ohm values, and power values. So imagine we've done something like this. Imagine we've gone to Radio Shack and we've bought ourselves a bunch of resistors, and they happen to be only 1, 10, 100, or 1,000 ohms, and they have various power ratings of 1 watt, 2 watts, 5 watts. We come back to the lab with a big bag full of resistors, and they're little individual packages. We've got 1,000 total resistors in our collection. And some well-meaning but precocious graduate student opens all of the little packages of resistors, pours them into a shoebox, and shakes my shoebox vigorously. So we know exactly the nature of the various resistors in our shoebox. They've just been randomized. We know exactly the possible values of ohmage, 1, 10, 100, or 1,000. And we know exactly the power ratings, 1, 2, or 5 watts. All right. So let's write down some probabilities. So we reach into our box and we pull out a resistor. The probability of drawing out a 1 ohm resistor is exactly 100 chances out of 1,000. So my probability is 10%, or 0.1. Over here, the probability of 1 ohm resistors is 100 chances out of our 1,000. Likewise, the probability of drawing out a 10 ohm resistor is exactly 500 chances out of 1,000, or 0.5, 50%. Probability of drawing out a 100 ohm resistor is 150 chances out of 1,000. That's 15%. And the probability of drawing a 1 kilo ohm resistor from the box is going to be 250 chances out of 1,000, or 25%. All right? So those are the probabilities of reaching into the bin and drawing out a resistor of a particular ohmage value. And this is true without regard for the various power ratings. Similarly, we could write down the probabilities of drawing out resistors of specific power ratings. So the probability of drawing out a resistor with a power rating of 1 watt is 440 chances out of 1,000, or 0.44, 44%. So there are 440 resistors total with a power rating of 1 watt out of 1,000. Likewise, the probability of drawing out a 2 watt resistor is 200 chances out of 1,000, or 20%, 0.20. The probability of drawing out a 5 watt resistor is 360 chances divided by 1,000, or 36%, 0.36. Everything that I've written on the board so far is what we know as marginal probabilities. Marginal probabilities. Marginal probabilities. These marginal probabilities are the probability of individual characteristics considered in isolation. Probability of the various ohmage values without regard for power values, the probability of various power values without regard for the particular ohmage value. So it considers one resistor characteristic in isolation. All right, marginal probabilities. The thing I'd want to observe, and this ties back to the first lecture, is since we only have 4 possible resistor values, and we know precisely the probability of each of those values, we can add those probabilities up, and we always get 100%. It's 100% likely to draw out a resistor whose ohmage value is either 1, 10, 100, or 1 kilo ohm. So it's a true statement that I can write down the probability of 1 ohm plus probability of 10 ohms plus probability of 100 ohms plus probability of 1 kilo ohm. Oops. Probability of 1 kilo ohm equals 100%. Likewise, probability of pulling out a resistor with 1 watt power rating plus probability of having a resistor with a 2 watt power rating plus probability of drawing a resistor with a 5 watt power rating is also 100%. So you'll notice that for my collection of resistors, I've got 2 different sample spaces. S1 is 1 ohm, 10 ohm, 100 ohm, and 1 kilo ohm. All right. This is the sample space for ohmage values. We also have a sample space describing the power ratings. S2 is 1 watt, 2 watts, and 5 watts. This is the sample space for power ratings. All right. Now, individually, S1 and S2 both contain a collection of mutually exclusive and collectively exhaustive values for each characteristic. So S1 and S2 individually contain a mutually exclusive and collectively exhaustive mutually exclusive and collectively exhaustive set of values in isolation. All right, for example, if I draw a resistor out of the box, if it's 10 ohms, that means it is not 1 ohm, 100 ohm, or 1 kilo ohm. It's one of the 4 possible resistor values, and only one of those possible resistor values. The set of ohmage values in S1 are mutually exclusive and collectively exhaustive. My box contains only 1, 10, 100, or 1 kilo ohm resistors. And when I draw a resistor out, it has a specific value that takes on one of those values and none others. That's what I mean by mutually exclusive and collectively exhaustive. Likewise for S2, describing the power ratings. If I draw out a resistor that has a 5 watt power rating, it is only a 5 watt power rating. It's not also 1 ohm or 2 ohms. Notice, however, that S1 and S2 are not mutually exclusive themselves. S1 and S2 are not themselves mutually exclusive. By that, I mean that I might draw out a resistor that's 1 ohm and 2 watts. And I might later pull out a 1 ohm resistor that's 5 watts. I might draw out a 100 ohm resistor that's 1 watt, and later draw out a 100 ohm resistor that's 2 watts. So S1 and S2 are not mutually exclusive, though the individual outcomes within each sample space are mutually exclusive and collectively exhaustive. All right, so since S1 and S2 are not collectively, not mutually exclusive themselves, we can start asking ourselves a variety of different questions. So I could ask myself this: what is the probability that I draw out a resistor and it is both 10 ohms and 5 watts? My shorthand notation will be probability of 10 ohms, comma, 5 watts. The word "and" will be represented by a comma in our future notation. This is what's known as a joint probability. right? The probability of this and that occurring, probability of reaching into my shoebox and drawing out a resistor that is simultaneously a 10 ohm resistor and also rated to dissipate 5 watts. Well, going all the way back to my my chart here, we have 10 ohms and 5 watts. There are 150 resistors that are both 10 ohms and 5 watts. So I can write that this probability equals 150 divided by 1,000, which equals 15% or 0.15. Now it's logical at this point, when someone's first learning about probability, to ask the following question. Is the probability of drawing a resistor that's both 10 ohms and 5 watts equal to the product of the marginal probabilities? All right, it's an obvious question to ask. The question is the joint probability equal to the product of marginal probabilities? All right? The probability of one characteristic taken in isolation is known as the marginal probabilities. Marginal probabilities are the probability of one characteristic taken at a time, and this is joint probability. Well, we can quickly do the math and find that probably 10 ohms and 5 watts. Put a question mark there. Is that the probability of 10 ohms times the probability of 5 watts? From our previous calculation, we know that this side is 15%, 0.15. And the probability of having a 10 ohm resistor from our earlier calculation is 0.5. And from our prior calculations, the probability of drawing out a 5 watt resistor is 0.36. And so clearly, %15 does not equal 18%. So in general, we can make a statement that joint probability cannot be found by multiplying marginal probabilities. If we go back over here, I should have put a question mark above that. We can say that that is not an equality. So in general, joint probability cannot be found by multiplying marginal probabilities. All right. Which leads us to our discussion of conditional probability. Conditional probability. We'll get back to this, the previous example in just a minute. I've got to introduce a new concept. What I'm about to write down is a true statement that is axiomatic, meaning that I can't prove it from more fundamental concepts. It's a true statement, it's axiomatic, I cannot prove it. What I need for you to do is recite the following statement over and over and over and over again until you're convinced yourself that it's correct. Here's the way it goes. Probability that I carry an umbrella and it is raining. It is currently raining. Is equal to the probability that I would carry an umbrella if it is raining times the probability it is actually raining. And I'll put square brackets around the right-hand side of my equal sign because the conditional probability with the if in it is multiplied times the marginal probability that it is raining. So what I want you to do is you can invent any scenario for yourself that you might like. This is the one that has worked for me over the years. I want you to just think about what I've written on the board here. Say it to yourselves over and over and over again and convince yourself that this is a true statement. The probability that I carry an umbrella and it is raining equals the probability that I carry an umbrella if it is raining times the probability that it's raining. Let me introduce these events. I'm going to say event A is the event that I am carrying an umbrella, and event B is the event that it's raining. Here again is I carry an umbrella and it's raining. B. I can rewrite this initial statement this way. I can say probability of A and B equals probability of A if B times probability of B. Probability of A and B equals probability of A if B times the probability of B. Even further shortened notation, probability of A comma B equals probability of A times a vertical bar B times the probability of B. So this vertical bar implies an if, and this comma implies an and. All right? Let's rewrite that a bit. Probability of A and B equals probability of A if B times the probability of B. This is a marginal probability. This is conditional probability. And this side is joint probability. Joint probability. Again, this is an axiomatic true statement. It's a true axiomatic statement. It is not, however, one of the three axioms of probability that I alluded to in my first video. So it's not one of the three axioms of probability that I mentioned in the first video. It is nevertheless an axiomatic statement, meaning that I can't prove it from more fundamental principles. All right. So it's by looking at conditional probability that I can actually get access to joint probability. And that was a question we were looking at just a few minutes ago. I might also mention that very commonly this relationship at the top of the page now is rewritten in the following form. And we'll use this quite a bit throughout the semester. And that is the probability of A if B equals the probability of A and B divided by probability of B. More often than not, we're going to see conditional probability introduced this way. So I want to highlight that. That's an important relationship that we're going to come back to many times. All right. So back to our example. Using table 1-2 out of our textbook, we can answer the following questions. What is the probability of drawing out a 10 ohm resistor if I know it to be a 5 watt resistor? Probability what's the probability of pulling out a 10 ohm resistor if we know it to be 5 watt rated? So for example, I reach into the box and I pull out a resistor and I show it to a colleague of mine and I say, I don't look at the resistor myself. I draw a resistor out of the box. I don't look at it. I don't look at the resistor myself, but I show it to a colleague and I say, what kind of resistor did I pull out? And my colleague's feeling like having fun with me, and he or she refuses to tell me the ohmage value, but says, well, I'm not going to tell you the ohmage value, but I will tell you that it's 5 watt rated. So I can now ask myself, what is the likelihood that I drew a 10 ohm resistor if I know it to be 5 watts? Well, I can calculate that using my joint and marginal probabilities. this can be written as probability of 10 ohms and 5 watts divided by probability of 5 watts. This, going back and looking at table 1-2, we'll find that this is 150 chances out of 1,000 divided by 360 chances out of 1,000. That's 150 divided by 360, and that is 0.4167 or so, truncated. Okay? Well, we might also ask ourselves this. What is the probability that the resistor I draw is 5 watts, given that my colleague tells me that it's 10 ohms? So I've reversed things. I've reversed what I know. In this case, I know it's 10 ohms, and I'm asking myself, what is the probability that it's 5 watts? I drew a resistor out. I didn't look at it myself. I show it to my colleague. My colleague's messing with me and says, I'm not going to tell you the power rating, but I will tell you that it is a 10 ohm resistor. I ask myself, what's the probability that I drew a 5 watt resistor, given that I now know it is 10 ohm? Well, you can do the math simply enough by looking back at table 1-2, and you'll find that this is 150 chances out of 500, or 0.300, and that is not equal to 0.4167. We can draw a general conclusion. In general, probability of A if B is not equal to the probability of B if A. In general. It's very important. All right. Well, back to my earlier question on conditional probability. We were asking this question. What is the probability of 10 ohms and 5 watts? Earlier we showed that we could not find the joint probability in most cases. There's a special case we'll get to in just a second. In most cases we cannot find joint probability by multiplying marginal probabilities. But we can find joint probability by employing conditional probability. So this can be written as the probability of 10 ohms if 5 watts times the probability of 5 watts. You'll notice whatever is on the right-hand side of my if bar, that's my if, whatever's on the right-hand side of my if bar shows up in my marginal probability. We calculated the conditional probabilities on the previous slide, and that is 0.4167 truncated times 0.36. That's a calculation we did early, very early in this lecture. And that turns out to be 15%, 0.15. The probability of 10 ohms and 5 watts equals 15%. Well, interestingly enough, I could calculate it this way. Probability of 5 watts if 10 ohms times probability of 10 ohms. Once again, what's on the right-hand side of the if bar shows up in the marginal probability statement. Well, if I calculate the probability of drawing a 5-watt resistor if I know it to be 10 ohms and multiply that times the probability that it's actually 10 ohms, I get 0.3 times 0.5, and what do you know? That's 15%. In effect, the calculation that I just performed is probability of 5 watts and 10 ohms. This leads me to the conclusion that joint probability is commutative. Probability of A and B equals probability of B and A. It's commutative. Joint probability is commutative. Expanding this out in terms of conditional probability, I can say probability of A if B times the probability of B equals probability of B if A times the probability of A. Okay? All right. Well, I alluded to the fact that there might be a special case. And that leads me to a short discussion, an introductory discussion of a concept known as statistical independence. Statistical independence. All right. It goes something like this. If the probability of A if B equals the probability of A, meaning that A doesn't depend upon B in any way, shape, or form, then we say that A and B are statistically independent. Events A and B are statistically So, for example, today, as I'm delivering this lecture, I'm wearing a blue and white striped shirt. That is absolutely positively independent of what you might be wearing. Your choice of clothing for the day is statistically independent from my choice of clothing for the day. All right? Events A and B, if they are statistically independent, that means they don't influence one another. They're not related. They don't. One doesn't matter in determination of the other. So I can also do some more mathematics. I can say that the probability of A and B equals probability of A if B times the probability of B. This is a general statement employing conditional probability. If they are statistically independent, probability of A if B equals the probability of A. And we find that the joint probability is the product of marginal probabilities. All right. If A and B are statistically independent, that means A doesn't depend upon B. The probability of A if B, the probability that A occurs if B occurs, is simply the probability that A occurs without regard for B. If that's true, then I can take my general statement here. It says my joint probability equals the product of my conditional and marginal probabilities. marginal probability is the probability of the event on the right-hand side of my if bar. Take my conditional probability and substitute probability of A. I get that if my events are statistically independent, that the product of the, the probability of the joint probability is the product of marginal probabilities. So, that's all for this lecture. If you have any questions, please feel free to contact me at your earliest convenience, and I'll do my best to answer and clarify for you. Thank you. Have a nice evening.